What the heck?
Hectogon.
Hello and welcome to another video. I have my trusty cup of joe. Oh, yikes. My hair is sticking up, that's really awful. Okay, so today we're going to cover the angle sum formulas for the trigonometric functions. There are four. One for sine, cosine, tangent, and cotangent. I'm not really sure why there isn't any for secant and cosecant. Perhaps they're just unwieldy to try and work with, because the main idea is that you want to put expressions for trigonometric functions applied to the sum of two angles in terms of trigonometric functions of only single angles, so that you can evaluate each of those individual pieces. And so maybe that perhaps just doesn't really work with cosecant and secant. I'm not too sure. Of course, naturally, they're just 1 over whatever the sine and cosine ones are, because they're the reciprocals of those. In this video, I'm going to cover the proofs for the sine and cosine angle sum formulas, and in the next video, I'm going to show a couple ways to prove the tangent and cotangent angle sum formulas. And then finally, once we've got all of the angle sums, we can move on to proving really interesting facts about the trigonometric functions, like the law of sines, the law of cosines, the angle bisector theorem, Heron's formula for the area of triangles. So it's going to get, a little more fruitful now that we've kind of covered all the really boring basics. All right, let's get to it then. All right, so as I said in the introduction, we're going to be covering these two angle sum formulas in this video, and in the next video we will cover the ones for tangent and cotangent, but for now we're just going to focus on these two. Let's take a look at what they actually say. It says that the sine of alpha plus or minus beta is equal to the sine of alpha times the cosine of beta plus or minus the cosine of alpha times the sine of beta. Now that's kind of a mouthful. What do those things mean? Well, first of all, plus or minus is an interesting piece of notation here, because which one is it? Is it positive or is it negative? What the symbol plus or minus means, or minus plus in this case right here, is that whichever sign you pick here, whether it's the one on top or the one on bottom, then the formula that you choose is the one that includes the option on top or on bottom, depending on which one you picked here. So for example, if I wanted to know the sine of some angle alpha plus an angle beta, I would want to pick the plus symbol here, and it would be the sine of alpha times the cosine of beta plus the cosine of alpha times the sine of beta. If I wanted the sine of alpha minus beta, it would be that, but minus that second term. And the same exact idea applies for the cosine angle sum formula, except it just so happens that when you pick the positive option here, you end up with the negative option here, and if you pick the negative option here, you end up with the positive option here. That's the point of the minus plus symbol. Minus or plus, because then it allows you to alternate the choice. Top option here is the same as the top option here, and they're the opposite here, right? So that just happens to be what the formula is like. Now, alpha and beta are any two angles or numbers that you want to plug into these equations. They could be positive, negative, complex, they could be anything you want, and these formulas will always hold. But today, we're not proving that. We're only proving it for where the sum of alpha and beta is between 0 and 90 degrees, or 0 radians and pi over 2 radians. Yes, Mom? So what I'm going to do is I'm going to present a geometric argument that will prove both positive cases, and we will actually use the fact that we know these are true to help us prove the tangent and cotangent ones in the next video. What I'm going to do to prove these statements is I'm going to draw a picture that's going to prove these facts for both positive options. So this picture is going to prove this plus that, and it's going to prove this minus that, right? So picking the top option in both of them, right? Plus and plus, you get a plus here, you get a minus there. So it's going to prove those two options, and then using facts about sine and cosine, I'm going to prove it for the minus option. We're going to use the facts that cosine and sine are even and odd functions respectively, which means we can do certain things with negative inputs, which makes our lives a lot easier. So we only need to do one geometric argument. So what I need to draw is I need to draw a rectangle. A rectangle. God, I can't even say that word without... Whatever. We're going to draw a rectangle. It's got to be relatively large so I can draw all the detail. Let's get that up. Wow, that's an awful rectangle. Okay. It's a wannabe square. I want a rectangle. Come on, Sam. Why can't you draw a rectangle? So that's supposed to be a rectangle. So these are all right angles. It's opposite sides are the same. Basic facts that we know, right? So what I'm going to do is I'm going to draw a couple of lines inside of this rectangle. So we're going to draw this line here. and this is going to bounce off of this wall at a 90-degree angle, creating a right angle here, and I'm just going to connect those 2 points so that we have ourselves a nice large right triangle here in the middle. And all I'm going to do is I'm going to assume that this length here, the hypotenuse of this right triangle, is of unit length. So from here to here is 1. And all we're going to do is we're just going to give these angles some labels. We're going to call this one alpha, and we're going to call this one beta. Now, you may have heard of the letter theta from doing trigonometry in the last few videos. These are just the first 2 Greek letters. Theta is a little farther down the Greek alphabet. They're just letters, right? This is like our A and our B. But Greek letters. And so Greek letters are very commonly used for angles, and so I'm just sticking to that convention. So now all we're going to do is we're going to figure out what the rest of these line segments are, as in their values, using trigonometry and the given angles. First, we need to recognize one thing. Because this is a rectangle, this side length is parallel to this side length, right? That's sort of a property of rectangles. And that means this line here that we've given unit length is what's called a transversal. Because these could be extended as 2 parallel lines, this is just a line intersecting both of them at the same angle, and so you get what are called alternate interior angles. So this whole thing from here to here is alpha plus beta as an angle, right? And it's a geometric fact that you learn in sophomore year that this angle is the same as this whole angle here, because this is a transversal intersecting 2 parallel lines, which means this whole angle is the same as this whole angle here. Since this whole angle is alpha plus beta, this whole angle is also going to be alpha plus beta. We have a couple angles labeled, and we just need to label one more angle actually, and then we are done labeling angles. So what we need to do is realize that because this angle is beta, and this is a right angle, since it is a rectangle, that this is also, why is everything so unlevel? Like, where's the bottom? Why is everything rolling from the middle always? Like, where's the bottom of the board? I don't get it. Since this is a right angle, that makes this a right triangle, which means that these 2 angles have to be complementary, which means they must add up to pi over 2 radians, right? Pi over 2 radians is the same as 90 degrees, so this angle and this angle must add up to pi over 2, which means this angle is pi over 2 minus beta, because pi over 2 minus beta plus beta gives pi over 2. And since this whole thing here is a straight line, all 3 of these angles have to add up to pi radians, because pi radians is a straight line, 180 degrees, right? So if this is pi over 2 minus beta, this is another 90 degrees, which is pi over 2, then we know that this angle in here has to also be beta, because pi over 2 minus beta plus pi over 2 plus beta equals pi. You can confirm that math for yourself, it works out, which means that this angle in here is also beta. So now we've labeled all the angles that we need to label to fill out the rest of this chart, and we will see our beautiful angle sum formulas. I love that my pens just roll in for no reason, and well, it's not no reason, it's gravity, obviously, but they just kind of have a mind of their own. I don't know what to do with them. What should we fill in first? Well, we remember that when we do the unit circle, and we do trigonometry in the unit circle, that all of our triangles have a hypotenuse of 1, just like this one. Which means that if we remember correctly, then this opposite side to the angle alpha is just the length, the sine of alpha, whatever that number is, right? So this length here, opposite alpha, is the sine of alpha, which consequently means that this line here, which is adjacent to alpha, is the cosine of alpha. And I hope that's easy to understand and see. I hope that makes sense. So now we're just going to fill out some other values. Take a look at this right triangle, which also has a hypotenuse of 1. Right? We can do the same exact kind of thing. So because this is a hypotenuse of 1 and this is our angle alpha plus beta, we know that the opposite side is going to be the sine of alpha plus beta. So we know that this opposite side is the sine of alpha plus beta, right? So, hey, that's kind of what we're trying to prove something about, right? Alpha plus beta. So hopefully something neat comes out of the woodwork. So I don't even know what the hell that means. But so similarly, this adjacent side to alpha plus beta is just going to give the cosine of alpha plus beta, because it is the adjacent side of the angle in a right triangle with a hypotenuse of 1, so it automatically, almost by definition, is the cosine of alpha plus beta. Just sticking to the color coding so you see where all of the values are. So this length right here is the cosine of alpha plus beta. So we've got our 2 things that we're trying to prove, which is more evidence to the fact that this one picture is going to prove both of the positive cases, right? We have 1, 2, 3, 4 more side lengths to fill in. Now we need to recall something. Remember, when we first learned about the unit circle, we rescaled everything so that the hypotenuses were 1, and that means that the legs just came out to be the cosine and sine of whatever the angles are. So because those things are scaled by by whatever the hypotenuse is, you simply need to multiply whatever the trigonometric values are by the hypotenuse just to get those side lengths. Now that may sound a little confusing, but think about it this way. If cosine of alpha were 1, if this were also 1, this length, then this triangle would have a hypotenuse of 1, which means this would be the sine of beta and this would be the cosine of beta. But this isn't 1, right, necessarily, right? It's the cosine of alpha, which means we need to scale both of these legs by whatever the cosine of alpha is, which means we need to multiply those legs by whatever the cosine of alpha is. So, simply put, the opposite side here relative to beta is going to be something times the sine of beta. In fact, it's the cosine of alpha times the sine of beta, because whenever you're doing the legs of a right triangle using trigonometry, you have to scale them by the hypotenuse. When the hypotenuse is 1, you're just multiplying by 1, so it doesn't change the values, and you just end up with sine and cosine, right? But because here the hypotenuse is not 1, it is the cosine of alpha, we have to multiply by that amount. So this is going to be the cosine of alpha times the opposite side to beta, so the sine of beta, right? So this is the sine of beta, right? And the same idea is going to happen here. It's the cosine of beta times whatever the hypotenuse is, which is the cosine of alpha. So this side length is going to be the cosine of alpha times the cosine of beta, right? And now we only have 2 more sides to take a look at, and the same logic is going to apply. This is beta, the angle is beta, the same here, but it just so happens that here the hypotenuse is the sine of alpha, not the cosine of alpha. So we're going to do the exact same concept here, just multiplying by the sine of alpha instead of the cosine of alpha. So this side length adjacent to beta is going to be the cosine of beta times whatever the hypotenuse is, which is the sine of alpha. So we have the sine of alpha times the cosine of beta. And the same idea is going to apply here. The opposite side is the sine of beta times whatever the hypotenuse is, which is the sine of alpha. So this side length is going to be the sine of alpha times the sine of beta. And, believe it or not, the proof is done. Because, remember, what shape is this? This is a rectangle. I keep saying rectangle, and I'm so conscious of how I'm saying rectangle that I keep saying rectangle, and I just want to hit myself for it. It's really silly. It's a rectangle. Rectangle. Jeez. I don't know why I can't say it right. This is a 4-sided shape with 90-degree angles and opposite congruent sides. How about that? I'll just be very wordy about it. Which means all of these are right angles, right? And opposite sides are parallel and congruent. So that's the important thing. Opposite sides are congruent. Which means that the sine of alpha plus beta is equal to the sine of alpha times the cosine of beta plus the cosine of alpha times the sine of beta. And that's proof number 1 done, right? This side length is equal to this side length. And therefore the sine of alpha plus beta is equal to this plus that. Exactly what my first equation said. And similarly, the cosine of alpha plus beta is equal to this length, the cosine of alpha times the cosine of beta, minus the sine of alpha times the sine of beta, just like I said. If this is the positive option, then we subtract the sine of alpha times the sine of beta. And now that we've proven those two things geometrically, again, only for angles between 0 radians and pi over 2 radians, but they do work in general, but this proof that I've shown you here only worked for those angles. If alpha plus beta is not between 0 and pi over 2 radians, then this proof is not valid for that. But remember, it really does work with any angle. We just need to sort of prove that in the future. Now that we've proven it for the positive option, right, the sum of angles, I'm going to use facts about cosine and sine, namely the fact that cosine is even and sine is an odd function, to prove the negative case. So let's do that now. Okay, so now that we've proven the facts about the angle sum formulas geometrically, in the positive sense, we need to prove it for the negative sense, right? So we've shown that if you ask what the sine or cosine of 2 angles added together, we've shown that those formulas are true. Now we simply need to show the negative case. I want you to recall something first. If we take a look at the right half of the unit circle, and we imagine some angle theta, and this is 1 because it's the unit circle, then this point right here is the cosine of theta, and this angle and the y-coordinate is the sine of theta. And I want you to imagine for a second that we do negative theta, right? So it's the same amount, just in the opposite direction. But you'll notice a couple things. If we plug in a negative angle, we have the cosine of negative theta, whatever that is, right? Comma, the sine of negative theta. But take a look. Since the cosine of theta is the x-coordinate of this point, and this point has the same x-coordinate, that tells us only one thing, that the cosine of negative theta has to be equal to the cosine of theta, right? The cosine of negative theta is equal to the cosine of theta. that tells you that cosine is what's called an even function. Now you don't need to worry right now about why it's called even and why the other one's going to be called odd. It has to do with powers of the terms that add up to this thing in what are called a Taylor series. It's an infinite sum representation of this. It's not anything you need to worry about right now. Just understand that even means when you plug in negative values to a function, you get the same thing as if you had just plugged in the positive values. And this isn't hard to see when you look at the graph of cosine. Right? We graphed it before. It looks like this. Things on the right give you the same value as things equally far to the left in the negative direction, right? Plugging in negative theta will give you the same thing as plugging in positive theta. So it's an even function, right? This is the cosine function, the wave. This is the y-axis and this is the x-axis, right? So it's sort of centered in the middle and it's reflective about the y-axis, right? It's a reflection of itself. And so plugging in negative values gives you the same thing as plugging in positive values. And so that's good. That's a good thing. The other thing we need to figure out is, take a look. The y-coordinate is exactly negative, right? So the sine of theta and sine of negative theta are not equal to each other in the same way that the cosine of theta and the cosine of negative theta are. In fact, they're slightly different. This actually shows us that the sine of negative theta is just the negative of the sine of theta. So that may be not clear when I say that. But unlike the cosine option, it's if you plug in a negative value, you just get the negative of when you plug in the positive value. And you can see that from the graph of sine, right? If I graph sine around 0, like I did before with cosine, you end up with this graph here, right? And plugging in some negative value gives you the negative of what you'd get if you plugged in a positive value. You could say it's one, if you rotated it 180 degrees about the origin, it would land right back on itself. So that's one characteristic. And then a function like this is called an odd function. And again, it has to do with its infinite sum representation because all of its terms are powers of x that are odd, just like all the terms that are powers of x for cosine are even. And so these are even and odd. Ooh, what the hell was that? And so these are called even and odd functions. Again, you don't need to worry about why they're called even and odd. Just understand when it comes to functions, even means plugging in negative values is the same as plugging in the positive value. And for odd functions, plugging in negative values is the same as getting the negative of when you plug in the positive values. And that's important. So these we have to keep in mind for proving the negative cases of the angle sum formulas. So I'm going to erase this now and we're going to get to it.